Hello everyone, welcome to Chapter 6, Section 3. Today we're going to be looking at multiplying monomials by monomials. If you guys recall, a monomial is a polynomial with one term. So really today we're just going to be taking two terms and multiplying them together to get one term. So let's go ahead and get started here. So we'll start off with a little rule here. So when we take two monomials, guys, and we multiply them, the rule of thumb is that we will multiply the coefficients and add the exponents. And most of us should remember this from 8th grade, as you did cover multiplying like bases. So you guys might have heard it called multiplying like bases, which is very similar to multiplying polynomials here. So if we take a look at example 1, it says to express in simplest form. So guys, what we're going to really do is just reduce these down, hopefully to one term. So we're going to reduce these down to one term. So if we look at A here, we've got two monomials, z to the fifth times z to the third. Now, if you guys take a look, both of these terms have a coefficient of 1. So we remember talking about that invisible 1. So we have 1z to the fifth times 1z to the third. Now, what I'm going to suggest that you guys do here is to kind of group the like bases together. So what I mean by that is I'm going to have you guys put the coefficients next to each other and then put the like bases next to each other. Oops. So really what we have here, and guys, what I'm using here is I'm using the commutative property of multiplication. If you guys remember what that is, the commutative property of multiplication says that we are allowed to rearrange the terms in a multiplication problem, which is what I've done here. Now, this makes it quite easy because now we can go ahead and multiply the coefficients. We get 1 times 1. This is pretty easy. It's just 1. Now, z to the fifth times z to the third, guys, z to the fifth times z to the third. Our rule of thumb is if we have like bases and we're multiplying them, we're going to go ahead and we're going to add the exponents. So what this is going to give us is z to the eighth. So our final answer is going to be 1z to the eighth, or if we just want to make it super simple, z to the eighth power. So guys, what we've done is we've taken two monomials, z to the fifth and z to the third. We've multiplied them, and we've gotten one monomial, which is z to the eighth. Now, a lot of you will say, well, I don't think I really need to do all those steps. You know, I can just see if I'm multiplying, I add the exponents. That's fine, guys. I'm kind of just taking you through, showing you the full process here. Once you get good, you won't have to perhaps use the commutative property. You'll just be able to identify the like bases and add the exponents. So, looking down at B, we have 4 monomials. A to the third, a to the first, a to the second, a to the first. Again here, guys, this is simply going to be, if we take a look, again, they're all like bases, A. We're going to go ahead and add all of the exponents. So this is simply going to, guys, they're going to have 4 monomials. This is going to end up being just one monomial. So 3 plus 1 plus 2 plus 1, that's going to give us a to the 7th power. Now, guys, understand that this monomial we're getting at the end is equivalent to the starting product. So a to the third times a to the first times a to the second times a to the first is the same exact thing as a to the 7th. A to the 7th is just simplified. So keep that in mind, guys. Keep that in mind. Okay, so we're looking at C here. Again, we have 4 monomials. Now, guys, this is where it becomes a little bit trickier because now we're dealing with multiple bases. We have bases in X and we have bases in Y. My suggestion here is to get the like bases next to each other. So I'm just going to go ahead and use the commutative property, and I'm just going to do a little bit of rearranging. So what this is going to leave me with here, guys, is x to the 3 plus 1 times y to the 2 plus 5, which if we simplify this up is going to be x to the 4th, y to the 7th. Now, guys, this is not a binomial. Remember, although there are 2 bases here, this is still a monomial because there's no addition or subtraction going on between the variables. This is just a larger monomial. Let's move on. So in D, we have 2h to the 3rd times 5h squared. Now, although we have parentheses around what appears to be 2 monomials here, we really don't need the parentheses, guys, because the only operation going on here is multiplication. So we can actually drop those if we want to and kind of just use multiplication signs. Now, if you didn't want to do that, I'm going to erase this, guys. If you didn't want to do that, what you could actually do is regroup these into 2 times 5 times h cubed times h squared. And by using parentheses, guys, it kind of keeps your work a little neater and helps you see the like bases a little bit easier here. So now it's just simple multiplication. So we have 2 times 5, which is 10. And then this is going to be h to the 3 plus 2, which is going to give us 10h to the 5th. Now, guys, some of you might, like I said, some of you might say, do I need to do this step right here? Do I need to do h to the 3 plus 2? No, you don't have to, guys. Like I said, I'm just showing you the full and complete method. That way, I'm not leaving any gaps in the explanation. Okay, let's move on. So looking at E, again, we have 2r to the 3rd s squared times r squared s. So again, guys, all I'm going to do is regroup these so that the like bases are next to each other. Now, I only have one coefficient really here, and that's 2, so I'm just going to group that by itself. Then I have r to the 3rd times r squared. And then I have s squared times s. Now remember, guys, that's really s to the 1st. So I'm gonna do the full process here. This is going to be 2 times r to the 3 plus 2 times s to the 2 plus 1. And guys, that's going to give us 2r to the 5th, s to the 3rd. Again, we end up with a monomial. Now, I know that, when we look at this, some of us want to say, well, this isn't a monomial. We've got an r and s in there. Guys, that's okay. There's no addition and subtraction to break this term up. This is just one larger monomial. 2r to the 5th, s cubed. Okay, looking at F. Very similar situation here, except we only have one variable, n. So again, guys, I'm going to group together our coefficients, in this case, -2 and -3. And then I'm going to group our like bases. N to the 5th times n to the -2nd. Now, hopefully at this point, some of us are questioning this second monomial here. This guy right here. And technically, I shouldn't even call it a monomial because if we remember from 6.1, in order for an expression to be a polynomial, its powers must be whole numbers. And if we look at that power of negative 2, that is not a whole number, guys. Negative 2 is an integer, but it is not a whole number. So technically speaking, this negative 3n to the negative second is not a monomial, and it's not a polynomial. However, we can still multiply out these two terms together regardless of if that second term is a polynomial or not, which it isn't, but we can still perform the indicated operations. And we're actually going to see something very interesting here, guys, in a second. So negative 2 times negative 3 is negative 6. And then I have n to the 5 plus negative 2. So I got a little plus negative up there in the power of n. And all that's going to give us, guys, is negative 6n to the third. Now, believe it or not, our ending monomial, that is a polynomial, because we do have a power of 3, and that is good for a polynomial. So believe it or not, guys, we took a monomial, and then we took a non-monomial, and we multiplied them together, and we actually ended up with a monomial. So let me repeat this one more time for you guys. It's okay if one of the expressions that we're multiplying by, or even both of the expressions that we're multiplying, are not polynomials. We can still perform the indicated operations even though they're not polynomials. Okay, let's proceed. So if we look at G, we've got 5 to the 5th times 5 to the negative 5th. Now, again, we would say that second one technically is not a polynomial. It's not a monomial. It's got a negative exponent. And there's no variables here. However, we still have like bases, which in this case are the bases of 5. So what we're going to do, we're going to do the same thing like whether or not that was 5 to the 5th and 5 to the negative 5th, or x to the 5th and x to the negative 5th. We're going to add the exponents, guys. We're going to add the exponents. And that's going to give us 5 to the 0. Now, we haven't talked a whole lot about these odd powers, 0 and the negative powers that we've seen. We will get to those, but we haven't talked extensively about them. But we did talk, guys, in 6.1 what that 0 power means. Anything to the 0 power is actually 1. So this product actually just simplifies down to 1. Moving on to H. So here it looks like we do in fact have, looks like this is two monomials here. And I don't see any negative powers. So it looks like these are definitely both monomials. And again, guys, regardless of whether or not I see fractions there's no fractions in the powers, which is fine. We can multiply by fractions. As long as those fractions aren't in the powers, they're still monomials. So I'm going to go ahead and just group these up. So I've got my coefficients of 1/2 and 3/4. Then I've got p squared times p to the 9th. And then I've got q to the 5th times q. And now we're just going to go ahead and we're going to simplify. 1/2 times 3/4, guys, that's 3/8. Here I'm going to have p to the 2 plus 9. And then I'm going to have q to the 5 plus 1. And our last step, guys, all we have to do is add those exponents up. So we're going to have 3/8 p to the 11th q to the 6th. And there it is, guys. We end up with another monomial. So again, guys, we're just really, the only new thing here is we're adding exponents. When you multiply like bases, you add the exponents. So on the flip side, this should make sense. When dividing monomials, we're going to divide the coefficients and subtract the exponents. So if you guys think about it, this kind of makes sense. If we multiply bases and we added the exponents, if we divide like bases, we're going to subtract the exponents. Makes sense. So let's start with a pretty simple example here. We've got b to the fifth divided by b to the second. So pretty simply, guys, I'm just going to rewrite this as b to the fifth minus 2. And that's going to give us b to the third power. And you know, guys, another way to think about this is if you've got b to the fifth, that's 5b's. Over b squared, that's 2b's. Guys, we can cancel 2b's from the top and bottom, which leaves us with b times b times b, which is in fact b to the third. It's in fact b to the third. Okay, let's look at a little bit more difficult one here. Let's look at b. So here we have 4g to the third h to the fifth divided by 2gh squared. Now guys, just like with multiplying, I am going to break this up and kind of keep my like terms grouped. So I'm going to make this 4 over 2 times g to the third over g times h to the fifth over h squared. And I'm going to go ahead and I'm going to simplify this. So 4 divided by 2 is 2. G to the third divided by g, guys, that's g to the 3 minus 1. Don't forget that this g here has a power of 1. And then it's going to be h to the 5 minus 2. If I simplify that, I get 2g squared h cubed. And there it is. Okay, now we've got 3 bases. 3 bases. So again, guys, I'm going to break these up. We're grouping those like bases together. And then we're using our rule, which says that if we divide like bases, we subtract their exponents. So this is going to be m to the 3 minus 5, n to the 2 minus 2, and t to the 6 minus 4. So if I simplify this down, I get m to the negative second, n to the 0, t squared. Now this can actually simplify a little bit more, guys, because if we recognize here, we got this n to the 0, and anything to the 0, if we recall, anything to the 0 power is equal to 1. So we can essentially just get rid of that because 1 times anything is what you had originally. So this is just going to be m to the negative second t squared. Now, typically, guys, we would not want to leave a negative exponent like that. First of all, if we look at that, we know, okay, well, that's not a polynomial. It's not a monomial because we have a negative exponent. So that breaks the rule. Regardless of that, we typically wouldn't leave a negative exponent floating like that. And some of you might be thinking, well, how are we supposed to get rid of the negative exponent? We will see in coming lessons how we take care of that negative exponent. But for now, we're going to leave it as is. So we're going to go ahead and leave that as m to the negative second t squared. Moving on to D. So we have t to the fifth over t squared times u to the fourth over u to the first. Again here, guys, t to the 5 minus 2, u to the 4 minus 1. So over here we're going to get t cubed, u cubed. And what you guys should notice here is as we go here, this kind of gets easier as we get the process down. The only thing they can really do to make this more difficult is add more terms, or add more variables, I should say. Like here in E, looks like we've got coefficients and then we've got 3 variables, so we've got 4 groupings to do. So that's 9 over 3, a to the 6th over a to the 3rd, b to the 4th over b squared, and c to the 10th over c to the 1st. So I'm going to start with my coefficients. 9 divided by 3 is 3. Then I'm going to have a to the 6 minus 3, b to the 4 minus 2, and c to the 10 minus 1. Which, if I simplify this down to my last step, guys, it's going to be 3a cubed, b squared, c to the 9th. And I end up with a fairly large monomial there. I will remind you again, guys, is this step completely necessary? No, it's not. Again, I'm showing you the full process here. You guys are more than welcome to skip that step, but I do suggest doing that the first few times you're doing the problems just to get the hang of it. All right. Now, this one's a little bit different because, as we can see, if we look in the numerator and denominator here, we have variables that aren't in both. For instance, we have an x up top and a w in the bottom, but there's no w in the numerator and there's no x in the denominator. So the question is, well, what do we do? I'm going to show you a couple of ways you guys can handle this. Number one being, you can just leave them where they are. You can just leave the x in the numerator and leave the w in the denominator where it is, and then simplify everything else. Or you can kind of take the following approach. So I do have a 5 in the numerator, and I do actually have a coefficient in the denominator, guys. Don't forget there's a 1 down here. So this is going to be 5 over 1 times t to the 4th over t squared. Now, what we can do here, guys, since x and w both, they're kind of they're not like bases, you can either leave them together like this, x over w, or you can break this up into x over 1 times 1 over w. It's really up to you guys. Now, as long as you know that those are not going to be, those are not like bases, you can just leave it as x over w. So now we're going to simplify. So 5 over 1 is 5. T to the 4th divided by t squared. Remember, that's t to the 4 minus 2. And then I can't do anything with this one, guys, because those are not like bases. So I'm going to leave it as x over w. So what I'm going to get here is I'm going to get 5t squared times x over w. Now, this is kind of weird because, you know, we've got this part of this term down here that's a fraction. So if we can help it, we'd rather write the whole thing as one big fraction. So what we're going to do is we're going to take this 5t squared and we're going to multiply it into the denominator. Or sorry, the numerator, I apologize. The numerator. So what that's going to give us, guys, is 5t squared x divided by w. Now, I'm sure some of you are thinking, well, if I leave it like that, is that wrong? No, that's not wrong. That's not wrong. However, if this was a multiple choice question, that might not be an answer. This will likely be an answer. So no, this one here is not wrong. It's not wrong, but technically this way here is the correct way to write it. All right, let's move on. So we've got another rule here for us. So we've done multiplying like bases, we've done dividing like bases, and now we're going to take a look at raising an exponent to an exponent, or taking a monomial and raising the whole thing to another exponent. So guys, when raising an exponent to an exponent, the rule of thumb is to multiply the exponents. We're going to multiply the exponents. So what do I mean by that? Well, let's take a look at A. We have x to the fifth raised to the third. So let me give you guys another way to think about this first before I show you the shortcut rule. X to the fifth to the third is x to the fifth 3 times. So this is x to the fifth times x to the fifth times x to the fifth. And what we can do here, guys, is we can use our rule when we're multiplying like bases. We add the exponents. So this is going to give us x to the 15th power. Now, a much simpler and quicker way is to use this exponent to an exponent rule. So what we're going to do is instead, x to the fifth to the third, we're going to go ahead and we're going to multiply those exponents together, and that's going to give us x to the 15th. So as you guys can see, both methods yield the same result. Okay, but we're going to go ahead and go with this shortcut method here. Now this does get tricky, and I will say that most of us will probably make a mistake here, and I will point out the mistake that most of us will make. So if we look at B, we've got 2y squared, the whole thing raised to the third power. So we've got this monomial 2y squared raised to the third power. Now, I know that a lot of you will just say, okay, well, I'll just do 2 times 3 and we'll get 2y to the 6th. Well, guys, here's the problem with that. If I write this out, this is going to be 2y squared times 2y squared times 2y squared. If we make that mistake, guys, we're completely neglecting the fact that there's actually 3 2's. We're completely neglecting that. So what we're going to have to do is understand, guys, that this 2 has an exponent as well. It's 2 to the first. So what we're kind of almost going to do here, and I hesitate using this word here, guys, but we're going to distribute this power to both exponents here. We're going to distribute this power to both exponents. So what this is going to be is 2 to the 3 times 1 y to the 2 times 3. And let me write this in the same order for you guys. Let me write this in the same order. So 2 to the 1 times 3 y to the 2 times 3. There we go. And guys, what that's going to give us is 2 to the third y to the 6th. And 2 to the third, guys, is 8. Oops, not 8, not y to the 8th. 8y to the 6th power. Now, I am going to point this out, guys, even though this is something that is going to come up later on this year. If I have a binomial raised to a power, I cannot distribute that power in. The whole reason why, guys, is this addition sign here. You cannot distribute a power over addition. However, you can distribute a power over multiplication. So this is the only time I'm going to tell you guys that it's okay to distribute a power through, is if you're distributing over multiplication. Okay, so let's see how this works again here. So in C, I have 5 to the first, x to the first, y to the third, all of that squared. Now guys, remember, this is all multiplication, so it's okay for me to distribute this 2 to all the exponents inside. So this is going to give me 5 to the 1 times 2, x to the 1 times 2, y to the 3 times 2. That leaves me with 5 squared, x squared, y to the 6th. And guys, we're always going to look to simplify this coefficient to a power here. 5 squared is 25, x squared, y to the 6th. And there's my simplest form. All right, let's move over to D. So again, I'm going to rewrite this, guys. 4 to the 1st, g to the 5th, raised to the negative 2nd power. Again, we can distribute over multiplication with the power. So this is going to give me 4 to the 1 times negative 2, g to the 5 times negative 2. So this is going to give me 4 to the negative 2nd, g to the negative 10th. Now 4 to the negative 2nd, guys, if you don't know what it is, which a lot of us probably don't right now because we haven't really talked about negative exponents a whole ton yet, 4 to the negative 2nd power is 1/16. Now, if you weren't sure of that, you could pop that in the calculator, and your calculator would tell you that it is 1/16. Now, as much as we would like not to have to leave this negative 10 exponent here, we are going to leave it for right now. We will cover how to take care of that negative exponent in upcoming lessons. But for now, we're going to go ahead and leave it 1/16 g to the negative 10 power. All right, so looking at E, looks like we actually have two different monomials being raised to a power. We have c squared cubed times 3c to the 5th to the 4th. So all I'm going to do, guys, is I'm going to rewrite this second one so that my 3 has an exponent. And then I'm going to distribute through. So this is going to leave me with c to the 2 times 3, 3 to the 1 times 4, and c to the 5 times 4. And I'm going to go ahead and simplify. So that gives me c to the 6th, 3 to the 5th, and c to the 20th. So some of you might notice that we actually have a couple of like bases there. We're going to take care of those in a second here. Let's start with this 3 to the 5th. 3 to the 5th is 243. Now, with these like bases here, I've got c to the 6th times c to the 20th. If you guys recall, when we're multiplying like bases, we're going to add the exponents. So this is going to be c to the 6 plus 20, which is going to leave us with 243 c to the 26th power. So let's take a look at this last one. Looks a little bit more difficult than the others. So again, guys, I'm going to go ahead and rewrite this so that everything has an exponent that I can see. And remember, guys, what that allows us to do is to easily distribute that power so we can see exactly where it's going. So we're going to have 2 to the 1 times 5, a to the 3 times 5, 3 to the 1 times 3, a to the 1 times 3, b to the 2 times 3. So it's going to be 2 to the 5th, a to the 15th, 3 to the 3rd, a to the 3rd, and b raised to the 6th. Now, here, guys, I've got two coefficients raised to powers. So 2 to the 5th power is 32. 3 to the 3rd is 27. So what we're going to do now is we have actually two exponents and we have two bases of a. So I'm going to do a little bit of commutative property here. I'm going to rearrange my terms. Sorry, I'm not going to rearrange my terms. I'm going to rearrange my variables and my coefficients. Because believe it or not, guys, this whole thing here, this whole thing is one term. How do we know that? Because there's no addition or subtraction going on here. So I've got 32 times 27, a to the 15th, a to the 3rd, b to the 6th. 32 times 27 is 864. I am going to shortcut this here, guys. A to the 15th times a to the 3rd is a to the 18th. And then I'm going to tack on my b to the 6th. And there's my simplified term. Again, guys, remember that this term here is the same thing as what I started with. So if I picked a value for a, if I picked a number for a and I picked a number for b, and I plugged it in here and I plugged it in here, I will get the same exact value. We just have to understand, guys, that this last line here, this guy here, is the simplest form for the product. It's the simplest form. All right, so let's take a look at example 4 here. It says, find the area of the triangle in terms of y. So this is a familiar question. We've seen this a couple times now. We should recall, guys, that the area of a triangle is 1/2 base times height. So we have our base, we have our height. So we're just going to go ahead and substitute those in. It says 1/2 5y squared times 4y. Now we're just going to simplify, guys, and we're going to kind of group up. I'm going to group our coefficients together, and I'm going to group my bases of y together. And what we're going to get here is 1/2 times 5 times 4, that's 10. Y squared times y, remember, guys, that's adding there. We're going to get y to the 3rd. So our area of our triangle is going to be a equals 10 y to the 3rd. Now, example 5 wants us to write x to the a raised to the b in another equivalent form, and then give a numerical example to show that the two forms are indeed equivalent. So, x to the a to the b. So the first thing, guys, here is it doesn't matter whether you have x to the a raised to the b or x to the b raised to the a. So believe it or not, guys, these are interchangeable. It doesn't matter what position they're in, because guess what? They're both equal to x to the a times b. So believe it or not, guys, all three of these are all equivalent. X to the a to the b, x to the b to the a, x to the a times b. Now let's show, using an actual number, why these are equivalent. So let's go ahead with a base of 2. Let's say 2 squared to the 3rd. So guys, well, 2 squared, that's 4. 4 to the 3rd is 64. So let's show that the opposite is also true. 2 to the 3rd to the 2nd. Well, guys, 2 to the 3rd is 8. 8 squared is, you guessed it, 64. Now let's show that that rule we've been using is also true. 2 to the 3 times 2. Or, not that it matters, guys, but 2 to the 2 times 3. That's going to give us 2 to the 6th, and 2 to the 6th is also 64. So as we can see, guys, it doesn't matter the order that the powers are in, you still come out with the same response. So finishing up here with example number 6, Sammy wrote a polynomial using only variable x of degree 3. So Sammy wrote a polynomial of degree 3. Megan wrote a polynomial in the same variable of degree 5. So Megan's was degree 5. Recall, guys, the degree of a polynomial tells us the polynomial's highest exponent. So Sammy's highest exponent in his polynomial was 3. Megan's highest exponent in her polynomial was 5. So the question is, what can you determine about the degree of the product of Sammy and Megan's polynomials? Well, guys, if we're going to multiply a degree 3 and a degree 5 polynomial, we can really keep this super simple and think about it this way. Sammy's polynomial could simply be x to the third, and Megan's could simply be x to the fifth. Now, I'm not saying that that's what they are, guys, but if we were going to keep it super simple, they could easily be that basic. And just this thought process here is going to help us understand the degree of the new polynomial, because if you guys recall, what we're going to do here is we're going to add the exponents together, leaving us with x to the 8th. So that means our new polynomial, guys, is going to be of the 8th degree. So guys, we learned 3 new rules today, and they are as follows here, and I'm going to kind of add a new page in here and just recap this really quick. Remember that when we multiply like bases, x to the a times x to the b, that we add those exponents together. When we divide like bases, x to the a divided by x to the b, we subtract those exponents. And when we take a term, x to the a, and raise it to a b power of b, we multiply those exponents. And guys, remember, a and b can be any number, okay? Even negatives and fractional. Now, I know that we've talked in class that polynomials cannot have negative and fractional powers, but that doesn't mean that we still can't perform the operations with them. So understand, guys, that a and b can actually be any real number. Thanks for listening, guys, and I'll see you tomorrow.